not just the unit circle definition for our kind of basic trig functions, but really that right triangle definition for our trig functions, which is something that we've been doing over and over and over again. It was number 4 on the quiz. It was what we did on Friday with the letting sine of theta equal 1/5, so on. So really just more of that kind of idea that trig functions can refer not only to x values, y values on the unit circle, but also some kind of abstracted triangle statements as well. Before we get into those examples, though, the one definition that we are going to go over is for what are called the co-function identities. Now, again, this is not something that I am going to be testing you on procedurally. It's just something that I want to show you in case it comes up again, or if this is an observation that you have made, just to kind of clarify here. Now, what some of you may have noticed is that our outputs for sine and our outputs for cosine are very, very similar to one another, especially for kind of the critical angles that we've looked at. It is either, say, sine of theta giving us √3/2, or cosine of an analogous theta giving us √3/2, and so on. And so we get these similar but not quite the same outputs, and they also don't fall into the same order per se, just as we rotate around the circle. But there's a valid question there of when we are referring to our trig functions, do we need to have kind of two separate distinct functions? Could we instead have like one transformation on another, or is sine a transformation of cosine, or vice versa? And the answer is yes. There is a way to write our trig functions as transformations of one another. This applies not just for sine and cosine, but for cosecant and secant, for cotangent and tangent, hence why these are called the co-function identities. But essentially the way they work is if I have cosine of theta, this is the same as having sine of pi/2 minus theta. If we want to understand the transformation that is going on here, notice we've got a lot of stuff going on the inside of our function, so a whole bunch of horizontal transformations. In particular, we are shifting by pi/2 in some direction. In this case, think of, rather than starting at the positive x direction, to start at pi/2 would mean we're starting in the positive y direction, and then we are subtracting away theta, so rotating clockwise rather than counterclockwise around the unit circle, and the claim is that that will swap the x and the y values. Right? Cosine of theta would give us the x, sine of theta gives us the y, and the claim is that those flip with this kind of inversion here. You can do the exact same thing in the other direction as well. So sine of theta should also be cosine of pi/2 minus theta. And then, like I said, you can do this with all of the co-functions. So cosecant of theta is secant of pi/2 minus theta, and so on and so forth. You could generate the other three yourself fairly easily. It's a little bit too specific for my tastes, again, just as far as like things that I would assess you on directly. But they do exist, and really I just wanted to use them to kind of tie together the fact that, yeah, sine and cosine are transformations of one another. That is an idea that we are going to see very, very clearly in what we are going to be working with tomorrow, and really for the rest of the week. What would you think it would be? Give me a guess. Anyone want to guess? What would tangent look like? Yeah, it's sine over cosine. You could actually construct it from the fact that it is sine over cosine. You could prove what it would be. But just from our cofunction identities, how would I write tangent in terms of, let's say, its cofunction, cotangent? Pi over 2 minus theta. So tangent of theta would in fact be cotangent of pi over 2 minus theta. Exactly what you would hopefully predict. But again, if you want to prove that, just write out tangent as sine of theta over cosine of theta, and then replace sine of theta with cosine of pi over 2 minus theta, and replace cosine with sine of pi over 2 minus theta, and you get cotangent of, go figure, pi over 2 minus theta. Okay. Not very utilitarian, but again, just something I wanted you all to see. But ultimately, the focus of what we're going to be doing today does lie with our kind of right triangle intuitions of trig. So taking a look at example 1, we are given an angle and a triangle with which it is associated, importantly a right triangle, otherwise we wouldn't be able to do anything. And we are asked to find various trig evaluations for this particular angle. So we know cosine as far as our triangle definition. What is cosine as far as our triangle definition? X over R. Or we could think of this as like the adjacent over the hypotenuse. Either way is totally fine. We've kind of trained ourselves now to think of adjacent as being like the x value and the hypotenuse as being the r value. Now, of course, that is only the case when the angle that we were referring to, like this alpha here, is this central angle, which is exactly what we see. We could also think about what's going on, say, from this angle here, where now our opposite side would be x instead of y, and our adjacent side would be y instead of r. But that is why standard kind of traditional setup does have it from this kind of consistent way of letting the angle be the central angle here. All right, and so what is our value of x? What is our value of r? What is this going to be? 15 over 17. Cosecant was one of our new ones. What was cosecant of an angle? How did we define this based on what we already knew? Okay, so we could think of this as r over y. Where did that come from, r over y? It's the reciprocal of sine. This is like 1 over sine of a particular angle, but r over y is a perfectly good way to think about it. Hypotenuse over the opposite side. What in this case is r over y going to give us? 17 over 8. Geniuses. Perfect. All right, and tangent, we had our kind of new definition for tangent. What was the new way that we defined tangent? In terms of our basic trig functions? Sine over cosine. So sine of alpha over cosine of alpha. And you certainly could do this 8 over 17 over 15 over 17 and then simplify, clean that up. But what is kind of our newfound, or not our newfound, but the faster way to use this as a ratio? This is going to be opposite over adjacent, or y over x. This is 8 over 50. All right, questions with example 1. Hopefully pretty much par for the course from what we saw on Friday. Honestly, even easier than the triangle constructions that we were doing on Friday. All right, then let us take a look at example 2. Nothing different than what we did in example 1 with example 2. It's just rather than giving you the triangle, you're going to have to set up the triangle yourself. But that's not too bad. In this case, we were told that a right triangle has an angle of pi over 3, and a hypotenuse of 20. We are trying to fill in the rest of the information. What else is going on here? Okay, so we've got our right triangle. Like so, where we know that this angle, we'll call this pi over 3. Of course, you can call the other angle pi over 3 if you want, but again, it's just a little bit easier, I think, to just think of all of this in terms of the central angle. Now, talking about triangles with angles and radians, that can be maybe a little bit tricky, but ultimately not too bad. What is pi over 3 as a degree? That's 60 degrees. So what kind of triangle are we looking at here? 30, 60, 90 triangle. So this other degree, or the other angle here, just to keep it consistent in radians, we know it's going to be 30 degrees or pi over 6 radians. And then what else do we know? Well, we know the hypotenuse, or r, is going to be equal to 20. All right, so what are we missing here? Well, we are missing our value for x, or our adjacent side, and our value for y. A couple of different ways that we could approach this. First and foremost, we actually have formulas for x and y. Right? But what if we don't remember those formulas? Well, one, we should probably learn those formulas. They're not going to go away. They're going to be very, very important in the coming weeks. So it's probably a good thing to learn. But like, let's say we forget our formulas. What can we do then? Well, what ratios could we construct from what we know with what we don't know? For instance, if I'm trying to figure out what y is equal to, can I construct a trig statement using the angle that I know and the side length that I know? And if so, what trig statement would that be? So let's start with this. What side length do we know? R. We know the hypotenuse. Okay. What did I say the side length that we're looking for is? Y, which is the opposite. What trig function or functions do we know that incorporate both the opposite side and the hypotenuse, or y and r? That's going to be sine. Okay, so we know that sine of theta should be equal to y over r. If we are solving for y here, how could I rewrite this to be useful? Well, y should be equal to, this is the formula that we should know, r sine of theta. If y is equal to r sine of theta, what is x going to be equal to? R cosine of theta. Very good. We know what r is. We know what theta is. This is going to be equal to 20 times sine of pi over 3. Over here, this is 20 times cosine of pi over 3. What is sine of pi over 3? Root 3 over 2 times 20 gives me 10 root 3. And what is cosine of pi over 3? 10, well, 1/2 times 20 is 10. So drawing our triangle and then identifying what is the relevant trig function that I need in order to figure out the missing piece of information here. In this case, when we were looking for y and when we know r, probably makes sense to use sine. If we were looking for x and we know r, then it probably makes sense to use cosine. All right, questions here with 2a. All right. Let's take a stab at 2b. Take 5-10 minutes. I would highly recommend for these styles of problems drawing a picture. It'll just ground you, make it easier. What am I looking for? What am I missing? What do I know? So on and so forth. Pay in particular attention. What trig function would make a lot of sense to use based on what I am looking for and what I am given? Not to say that there's not more than one way to solve this, but there is a fastest way to solve it, which we'll find by identifying that piece of information, and then plugging into your calculator. Make sure your calculator is in radians when you're doing this. Of course, if you wanted to leave this as an exact answer, I would not fault that. But if we are going to round here, which this one would be an okay one to round, then that's totally acceptable. So take a moment, focus on drawing. What is this going to look like? What am I missing? What am I given? Going from there. setup looks good. So what do you solve for here? Yeah, so we're looking for arm. And then which of these two do we know? That one is 5 5 12. Sounds good. Okay, this looks good. So what do we have here? Is this a y value or x value? Well, it's actually, it should be a y value that you have it as the position. So you're right that it is, like your setup, your picture looks good. No, your picture looks good, right? Because we're thinking about. It's just mislabeled. Yeah, you just mislabeled it. Yeah. And so instead of using cosine, yeah, we'll use. Okay. Looks good. Solving for h. Yep, looks great. Let's start. That looks perfect. You have a question? So if you're going to use the degrees, then do it. Are we dividing by 5 5 or 12? Are we dividing by theta? Sine theta. Okay, this looks super good. What are we looking for here? What are we missing? So we're missing R. So your setup here for finding x, perfect. Totally worth it. In this case, finding x is not like bad, it's just overkill, it's just unnecessary. So what trig function would we use to find R? Yeah, we use it. Like again, your setup for finding x, perfect. It's just x. We don't need this with those. Perfect. Yeah, this looks super good. And then sine of. Okay. Looks super good. We definitely could use cosecant, and this would totally work. And you would get like sine, or well, you would get r over 50, and then like multiply this up by 50. Cosecant, just because there's not like a cosecant button on our calculator, is going to be a trickier one to use. So whenever we have the option of either using sine or cosecant, we generally default to sine. But again, there's nothing wrong with using cosecant, and ultimately you get the same thing. Here's a good, you just need to plug in the numbers, and then the actual cosecant bit is maybe a little bit tricky, but you can always do like, for instance, if I want to evaluate cosecant of 5 5 or 12, you always do 1 divided by sine of 5. And that would give you cosecant. So that is your. Yes.
This is yes.
I agree.
Okay, but how would we simplify this to really be, I'm assuming we're right?
No, you're not going to have to get values here. We're going to look at 5 5 or 12. 5 5 or 12. It's not on a unit circle. If it was on our unit circle, I would want like exact values. As it stands right now, and until we get to unit 5, we're not going to be able to deal with like the over 12, like
So
5 or 12.
I'm gonna write it as just this weird fraction.
You can just honestly write it as 51 point
7 times 6. That's perfectly fine. You could also leave it as 50 over sine of 5 pi over 12 if you wanted to be exact, and that would be perfect. I would do that for sure.
Okay, let's take a look here. Overall, looks really, really good. All right. So the picture that we saw, that I saw from many people, looks something along these lines. We've got our building here, and we've got our ladder up to a certain part of our building, where this is our right angle. And we are given a theta from the ground. So this particular theta here, which we are told is 5 pi over 12. We're also told the height that that ladder needs to reach. It needs to reach a window that is 50 feet above the ground. Okay, and we were looking for the length of the ladder. So between R and X, which one corresponds to the length of the ladder here? R is going to be the length of the ladder. So looking for our radius here. Which trig function are we going to use that incorporates the known information of the opposite side 50 and the thing that we are looking for, the missing radius or the missing hypotenuse? Okay, sine of theta is going to be the trig function that we can use, and we certainly can set this up as y is equal to r sine of theta. Now, could I have also used cosecant? Yeah, absolutely. Cosecant is r over y instead of y over r. There's nothing wrong with that. The only thing that's quote unquote wrong with that is that there's not a cosecant button on your calculator. Thank you. So logically, nothing wrong with it. Certainly if we weren't going to simplify, right, because we don't necessarily need to simplify, we wouldn't need to use, there's not really a difference between sine and cosecant. You certainly could use cosecant here as well. Sine is probably just the more natural default because we have a sine button on our calculator. Yes. On your calculator, 1 over cosine. We'll get you secant. Same with like 1 over sine. If we wanted to do, and we'll see here that the solving process, we end up dividing by sine. You get the same thing multiplying by cosecant. So it ends up being the same thing. All right. We, of course, do not want y. We are looking for r. Dividing both sides by sine, we get that r should be equal to y over sine of theta, which, just as an aside, is the same as saying that r is equal to y cosecant of theta. Again, you can use cosecant here. It's totally fine. It works. There just isn't a cosecant button, but you can do 1 over sine, and that would work. All right, so that's perfectly acceptable. And plugging in the numbers that we know, this is 50 over sine of 5 pi over 12, just making sure that your 5 pi over 12 is in fact or that your calculator is in radians if you were going to do this, because we were given the theta in radians. You can totally leave your answer like this. 50 over sine of 5 pi over 12 feet is correct. That works. But you can also plug it into your calculator and simplify. This is equal to about 51.76 feet. Questions with 2b? hopefully not very different from what we were doing on Friday. Actually, hopefully exactly the same thing that we were doing on Friday, pretty much. Just now the added complexity of you're going to need to pick your trig function that will work. And just thinking through like, okay, what do I know? What am I missing? We'll do 2C for our bell work on Tuesday, tomorrow. And then we have a very fun section starting with graphic, which will be entertaining. Yes. Not really. It's the other 6 trig functions are all just in terms of sine and cosine. So we just defined, and it's basically the same thing we've been doing. We just have like more definitions. So just knowing that like tangent is sine over cosine, that cosecant is 1 over sine, that secant is, but otherwise it's the exact same thing. Yeah.
I just want to know, since I wasn't here when you explained it.
Yeah, it's not too bad. But also during tomorrow after your quiz, if you wanted to take a look at some of this, I'd be more than happy to. Yeah. All right, and I should have the lecture uploaded. If not tonight, probably not tonight, but tomorrow it should be up. Yes. Yes.
I know you got like 10 square thing.
Square root of 3. Mm-hmm.
How did you get that? Because I got like 17 something. And if I do 10 square root of 3, it gives me the same answer. Like,
yeah.
Is it where you convert it on the calculator?
So you can't convert on the calculator with the square roots. So what you can do instead, so sine of pi over 3, that's from the unit circle. So that's one that you just kind of need to memorize, that sine of pi over 3 is going to be root 3 over 2. And then 20 root 3 over 2. So if we do 20 times 20 times root 3 over 2. You can totally write this as 20 root 3 over 2, and I would take that. That simplifies to 10 root 3 because the 20 and the 2.
My second thing is, how did you get like any of this?
So we know that sine of theta is y over r, right?
Yeah.
Okay. So what happens if we multiply by r on both sides? Well, we get that y is equal to r sine of theta.
Oh, we had to multiply.
Yeah, so multiplying by r on both sides
like
is how we get that.
y meant it could also be like meaning sin if it was like on the.
So if we're on the unit circle, r is just 1. So when r is 1, we get exactly that y is sine. That y and sine are the same thing. But r can also be something other than 1. It could be 2 or 20 or something else. And so when it is that, we just multiply by whatever that radius is.
I think that cleared up some of my confusion.
Perfect.